Hello, everybody.
Hello. So we can hear and see each other?
Yes, I can see Joris and Giron.
Yeah, indeed.
I can see Alejandro.
Yeah. Yeah. Can you hear me? Okay. Yes. So
Yeah.
Gamaliel is here. Jeroen, Joris. I think we need to wait for Hector Puebla and Olaf.
Yes, perfect.
Okay. Mira, pues ya no entendí. ¿Hay cámara de video? ¿No hay cámara de video? ¿No? Ah, ok. Porque luego, bueno, no sé si me van a decir algo de.
O sea, sí tiene cámara, pero no sé, te
Ah, ok.
tendrías que poner aquí para que te vean.
Ah, ok. No, es que no sé si. Bueno, se puede poner la cámara como para que me vean, porque no sé si sea como algún tipo de requisito que. Ujú. Sí, desaprendió. No, un poquito. Bueno, prende la cámara, prende el video. ¿Cómo sé que me están? Ah, ya. Sí, ¿no? Ajá, va.
Yes, now we see you indeed,
Yeah, okay,
Alejandro.
perfect. Okay, we'll do something like this. Okay, yeah. Okay, this. Okay. Ah, falta Héctor y Olaf. Los que faltan. Sí, 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 sí. Um, ah, ya la regué. ¿No? De pronto. Can you see the screen of my presentation or are you seeing something else?
Yeah, no, we
Uh,
see the screen of your presentation.
Okay, perfect. Thanks. Okay. Yeah.
Hello, good afternoon, Olaf.
Hola. Sí.
Hey. Hi, good afternoon. Do you hear me?
Hello, Professor. Listen. Hello, hello. Mark. Yeah, Mark is here too. And sí, solo falta Héctor. Héctor Puebla, yes. Ah, bueno, sí, sí. Okay. ¿Empiezo? Ah, ya, ya, sí. Bueno, ¿me escuchas? Sí, sí. ¿Sí se escucha, doctor? ¿Sí, verdad? Sí, sí, ok. Ah, ok, va. Sí, está bien. Ok. Sí, ok. No, sí, ahorita me dijeron que sí. Ah, que sí, ellos escuchan, o sí, no. Ah, sí. Ah, sí, no, ahorita, de hecho, saludo. Ujú. Ujú. Sí, sí. Ah, falta Héctor. Sí, pero es...
No recuerdo el convenio.
pero, ¿cuál es el detalle?
Es que en nuestros lineamientos deben de haber dos internos más para que inicie el examen. Solo está Richard.
Ah, no, pero también cuenta Gante. Son dos internos, o sea, de... o sea,
No anticipo.
ah,
Los internos no. El detalle es que si recuerdo si en el convenio había una cláusula relacionada con el interno para que se lleve el examen.
pues que yo recordaba que decía nada más dos internos, o sea, uno de cada institución, pero no sé si aplicaba a la privada o a la pública.
Es que ese es. ¿Traes por ahí el convenio?
No es que no es mi laptop, yo la dejera. Es el artículo 15 o 17, creo, del convenio. ¿No te,
Arriba de los lineamientos. Sí, claro.
te dijo algo Héctor o...? Sí. Ok, ok. Sí, sí, sí. Well, hello everyone. Dr. Hector Puebla is just coming. In 1 minute, he will be here online. So just thank you for your patience again. Sí. Sí. Yo pensé que íbamos a ser como 5. No te dijo nada más, Héctor. No te dijo nada más, Héctor. No,
Gente, ¿no?
¿Eh?
2 minutos.
¿Eh?
Pudo no haber dicho.
Con todo el historial que hay. Ya. Ok. Ok. So everybody's here. Yeah.
Okay, great.
Yeah. Good morning. Sorry for the delay.
Afternoon, Europe.
Good morning, no problem.
I welcome all to the doctoral examination of Alejandro Romero Limones as part of the joint doctorate between Ghent University from Belgium and the Metropolitan Autonomous University from Mexico. Before we begin, I would like to provide some information about the protocol process that is followed for this examination. The examination consists of 2 consecutive stages of parts. A first meeting followed by a public defense. The first meeting took place in Ghent University on May the 30th of this year, and in which Alejandro Romero, the examinee, gave a brief overview of his research, which was followed by questioning from the members of the examination board. Then, after deliberation by the examination board, Mr. Romero was admitted to the second part of the examination, that is the public defense of the doctoral dissertation, which has us gathering in today. So today at Metropolitan Autonomous University, we are attending the public defense of the doctoral dissertation submitted by Alejandro Romero Limones to obtain the doctorate academic degree from each of both universities. Yes, Ghent University and Metropolitan Autonomous University. The title of his thesis is Innovations of Hydrocarbon Valorization, a comprehensive study of the oxidative conversion of methane and the oxidative dehydrogenation of ethane. His supervisors are Professor Carlos Castillo Araiza from Metropolitan Autonomous University and Professor Joris Pibot and Dr. Jérôme Poissonnier from Ghent University. Now I would like to welcome the members of the examination board, which are as follows: Professor Max Sayes from Ghent University, which is participating online. Professor Kai Olaf Henriksen from Technical University of Munich also participates online. Professor Gamaliel Che Galicia from the meritorious Autonomous University of Puebla. He's also connected online to this exam. Professor Héctor Fernando Puebla Núñez from Metropolitan Autonomous University is connected online. And myself, that I've been appointed as chair to this exam, Richard Ruiz Martinez from Metropolitan Autonomous University. Now, I welcome all the audience to this public examination. I would like to inform that the present examination has been made available via a live stream to all those who are unable to attend this public defense in person. So now we are going to step to the oral presentation. I will ask Mr. Romero Limones to present his work in not more than 45 minutes, if you please.
Okay.
Thank you.
Okay, thank you. And well, first of all, thank you everyone for coming here. I know it's a little bit early here in Mexico, and good afternoon everyone in Europe, and for those who are following this public defense via YouTube or Zoom. So in the following presentation, I will show the main contributions obtained during my PhD between UGent, between UGent, Ghent University, and UAM-Iztapalapa. So the title of the thesis is Innovations in Hydrocarbon Valorization, which was focused on two main hydrocarbons, methane and ethane. Right? So from the methane, the oxidative conversion of methane, and for ethane, the oxidative dehydrogenation of ethane. So, well, just 1 minute. Can we just remove the part of the top of the screen? Is there? Yeah, we have a technical issue. I don't know if I can.
Online, we can see it perfectly well.
Okay, sorry. Yeah, but here in the room, yeah, like the bar from Zoom is it's blocking the title of the slide. No, it's not possible. Okay, well, I will continue like that. Okay, so yeah, first valorization of methane. So what has been done on the valorization of methane? Well, we can go to the 80s, early 80s, where the oxidative coupling of methane was proposed as an alternative to valorize methane. This means we oxidize methane to produce ethylene. However, since this moment, almost all the entire periodic table has been studied, trying to find and to synthesize a suitable catalyst to, well, yeah, to achieve the goals for OCM, which are achieve C2 yields, and also most of the C2 yields to the ethylene. So this has not been possible yet. And one of the alternatives proposed in this thesis is the oxidative conversion of methane. So please do not confuse OCM with OCOM. Yes, OCM is oxidative coupling of methane, while OCOM is the conversion of methane. So OCOM arises as an alternative in the C123 project. I will talk about that later, in which we wanted to harness the side reactions. I mean, not only ethylene, but the production of CO as a feedstock for a further process to produce C3 species. Now, regarding valorization of ethane, yeah, a little bit of history. We can go to the end of the last century, yeah, the 1999, where a milestone in America occurred, the shale gas revolution. So in the shale gas revolution, the wells that contains ethane from natural gas were exploited increase the exploitation of these wells. So since this moment, the steam cracking of ethane to produce ethylene arises among other processes. However, this steam cracking of ethane to produce ethylene is a highly endothermic process which requires high temperatures as 100 degrees. And another issues that we can find here is the CO2 production or the coke formation. So as an alternative, proposing this thesis, we have the oxidative dehydrogenation of ethane, which is ethane producing ethylene via the oxidation. So this is an exothermic reaction that with a suitable catalyst can take place at temperatures below 500 degrees. And as a funny fact, when I started my PhD, this reaction was not commercialized. And in the last years in Germany, Linde company commercialized this reaction. And in China, the Dalian Institute made some pilot plant tests, and the results were positive, and they are pretty confident that they will scale up this reaction. So the reaction works. This is something good. However, the model to describe the reaction, mainly the reactor, is something else that we should take care, because the high parametric sensitivity to describe hotspots or the runaway situations is a matter that we should take care. So we need to have a reliable reactor model. So saying this, you can see that the thesis, the thesis, the work, and this presentation is divided in two main topics: OCOM and ODH. So let's talk about first of OCOM. So for OCOM, as I said before, it started in the C123 project. This C123 process. Yes. So we have these unexploited resources that contains a huge amount of methane, and also we can have biogas, shale gas, other natural gases, right? So it goes to this OCOM reactor, which in this part of the process is, for the moment, a black box. And then the goal of OCOM is to have an outlet stream with an optimal mixture of CO and ethylene. This means an equimolar mixture. We want high yields of ethylene, but also this equimolar mixture between CO and ethylene. And then it goes to, the stream goes to an hydroformylation reactor, to harness this mixture of gases to the production of C3 species: propanol, propanol, propylene, polypropylene. This is like the main goal of the C123 process. But I was focused here on OCOM in this part of the process. So for OCOM, the first task was to select a suitable catalyst that, which could have a high selectivity to ethylene, but also to CO, high yields. So the catalyst selected was this, a manganese sodium tungsten supported on silica. Yes, it should be noted that other catalysts were tested, but this was the most promising catalyst. So with this catalyst, some experiments were carried out in the LCT, in the care group from Professor Thibaut in the LCT. So the data collected in the lab showed that the catalyst, had a nice selectivity towards ethylene and also to CO. But something that also was interesting was the low selectivity to CO2. So that means that the conversion of methane goes mostly to ethylene and also to CO. And something else that we saw that was that the CO2 co-feeding has not a significant effect. So with these experiments, we proposed these 12 reaction steps kinetic network. So you can see here 3 oxidative reactions of methane that produce ethane, CO2, and CO. 3 oxidative reactions of ethane that produces ethylene, CO2, and CO. 2 oxidative reactions of ethylene to produce CO2 and CO, the total oxidation of CO, and because the high temperatures that we have in this process, well, in this reaction, the thermal deterioration of ethane, this means ethane producing ethylene, was also considered, and because in all these reactions, water is produced, the steam reforming of methane and also the water gas reaction was considered in the kinetic network, right? So, yeah, we also propose preliminary kinetic model with these rate equations when the activation energy and also the exponential factor were the parameters to be estimated. And then the reactor model, the contribution factor equation, and the integral reaction rates. Here, I would like to say that an analysis of the reaction rates was carried out, yes, but considering this integral reaction rate, it means that we capture the effect of the reaction during, from zero to the waste of the catalyst. So here you can see the parity plot diagram, and you can see that the experimental data and the simulation, well, the simulations fit in a good way with experimental data. Then here you can see the parameters estimated, I mean, the pre-exponential factors and also the activation energy. And the figure from the right shows the impact that the different reactions, well, the different reaction rates have between each other. So here what we can see is that 4 of these 12 reactions were not significant in comparison with the other reactions. And also the estimation of these or the parameters for these reactions were not statistically significant nor physically. So based on these criteria, we decide to remove these reactions, and instead of having a 12 reaction network, we just keep 8 reactions from this reaction network. So with this kinetic model, some simulations were carried out in order to see the impact of different operating conditions, temperature, methane to oxygen inlet ratio, or the space-time, also the effect of co-feeding ethane. But for this presentation, I will only show the effect of temperature. So you can see here that if we increase the temperature, the conversion of oxygen increases, which is something that we desire for the outcome reactor, because we wanted, well, the minimal amount of compounds in the gas mixture. And then, we also have the increase of methane as the reaction is increasing. Yes. And, we can see also the same trend with the yields of the different carbon species, but ethane. So why is that? Why, as we increase the temperature, all the carbon species yields increases, but ethane? So to understand this trend, we could go to the reaction rate plot. So in this reaction rate plot, please note that, also in the bottom part of the slide, you can see in yellow the reaction that produces ethane. So in black, the reaction that produces CO. In red, the reactions that produces ethylene, and the gray is CO2. So if you look the picture, the figure from the right, you can see that the reaction that produces ethane, OCM, increases the reaction rates as the temperature increases. However, the reaction that produces ethylene, that means ethane reacting to produce ethylene, also increases as the temperature is increasing. And it becomes more and more important, especially the thermal deterioration of ethane. So this could explain why the yields of the different carbon species increases, but at this point, 120 degrees, more or less, kind of here, start decreasing the trend of the ethane yield and increasing the ethylene yield. So this same analysis was done for the operating conditions, trying to find an optimal operating condition for the outcome purposes. This means total conversion of oxygen, an equimolar mixture of the closest molar relation between ethylene and CO, and high yields for ethylene. So the results obtained show that these were in the box from the left show the optimal conditions found in this analysis from the simulations. A methane to oxygen inlet ratio of 10, temperature of 850 degrees, and space-time of 6.5 kilograms seconds per mole, and an evaluation of real simulation feedstocks was done for the C123 process or the OCOM reactor. So here, I would like to say that real simulation feedstocks means that we only consider, for example, in the case of natural gas, 100% of methane, for shale gas, 85% of methane, 8% of ethane, and 7% of CO2. For biogas, 64% of methane and 36% of CO2. And no contaminants were considered in these simulations. So the results are showing here. And you can see that the evaluation of natural gas, shale gas, and biogas are quite similar. However, shale gas is the most promising feedstock for the OCOM purposes. And you can see that the carbon conversion is the highest here, but most of the carbon conversion is because ethane reacts more than methane. This could be also explained because the strength of the bonds between carbon and nitrogen from methane that are the energy needed to break these bonds are higher than the energy bonds for ethane. So if we look at the figure in the bottom right, we could see that the yields of the carbon species, mainly ethylene and CO, is higher than the other feedstocks. And the molar ratio between ethane and CO, these green dots, is the closest one to one in comparison with the other two feedstocks. So it should be important to mention that these simulations were describing the OCOM reactor, but the main goal is to use OCOM reactor in the C123 process. So some considerations were also given to explore or to validate the C123 process. For example, we know that ethylene and CO are produced from the OCOM reactor and goes to the hydroformylation reactor. So these two compounds react, has 100% conversion in this hydroformylation reactor. However, the unreacted methane and CO2 from OCOM reactor, considering that CO2 is inert, both go to the hydroformylation reactor, and then both are also recycled to the starting part of the process. So some feedstock back calculation should be done, and because methane and CO2 are recycled, but mainly methane, we need to provide shale gas with higher content of ethane instead of the one we consider as 8%. So we can find in the literature that there are some shale gases with a composition of 16% of ethane. And also because CO2 is inert in this process, I mean, we cannot avoid an accumulation of CO2, so we need to purge this CO2 to prevent an infinite accumulation. And also, as the last comment, we need to also provide extra oxygen just to keep this methane to oxygen molar ratio. So with this, I would like to conclude and to give some perspectives from OCOM. So first, a kinetic model for OCOM was developed, and was also validated with experimental data, Some operating conditions were obtained. This means the temperature 100 degrees, some methane to oxygen inlet molar ratio, space-time, yes. So from the three real simulation feedstocks evaluated in this work, shale gas was the one with more potential among the others. This is because the yields of the C2 species, mainly ethylene of 30%, and because it's the one who has the closest ratio to 1 between ethylene and CO. And also some considerations to validate this C123 process. So some perspectives is that the kinetic model is a preliminary kinetic model. The reactor model was also isothermal model, a simple model. So this work proves that OCOM, could work, but more work should be done in order to explain or to scale up this process to the industry. So this is another opportunity for upcoming research. This means a more robust kinetic model, or another part in this process to consider the CO2 conversion to mitigate the greenhouse effect. And now we're going to the second part of this presentation, the one focused on the oxidative degradation of ethane. So here, the limitations of the reactor model are mainly focused on the transfer phenomena. So for example, most of the packet bed reactors, mainly those with a low two-to-particle diameter ratios, well, the models that are describing these packet beds or these reactors consider plug flow. What is plug flow? Plug flow means that the velocity in each radial position is the same. But because this void fraction in the packet bed, a void fraction profile is generated, and also it has a significant effect on the actual velocity. It means that at different radial positions, we have this radial profile for the actual velocity that has the highest velocity close to the wall, where the most important phenomena are occurring. Now, the description of the radial temperature gradients, mainly in this wall zone. Well, later in this presentation, I will give a more detailed explanation, but what I wanted to say here is that the main issue is to describe this green zone within the packet bed, the one with the highest temperature gradients. And if we cannot describe properly these temperature profiles, how can we be confident that we are describing the heat transfer mechanisms in a reactor? And then the role of the actual heat transfer, mainly the conduction in a packet bed reactor. So historically, this parameter has been neglected because the high particle Reynolds, or because the ratio between the length of the reactor and the particle diameter. However, we could see that the main temperature gradients, mainly the actual temperature gradients, occur in the inlet of the reactor. So an hypothesis came when I was doing the research to see if we can neglect the actual heat transfer conduction, or is it important to consider in the reactor model? So with these three, let's say, issues or the things to attend or to be focused, I did the research for the ODH reactor. So the procedure, first, the experimentation. I mean, we have a packet bed here in the laboratory here in Guam that we use to measure pressure drop or temperature gradients. Yes, and now with this experimental data, we go to the fundamentals. I mean, we go to the models to characterize this phenomena by some parameter, for example, for Ergun or Navier-Stokes, Darcy-Forsheimer, the alpha and beta parameters, or the effective viscosity. For the kinetic model, we took a kinetic model validated from the research group following an Ehlers-Riedel formalism. And then for the heat transfer, well, the actual effective conductivity, relative effective conductivity, and the wall heat transfer coefficient. Yeah. So we validated these models, well, the velocity and the temperature with experimental data. And now having confidence that we are describing properly velocity or temperature and incorporating the kinetic model, we can describe the performance of the reactor in order to know the hotspot prediction. So here I'm presenting the experimental data that we have here in the lab. Yeah, we used titania pellets of 8.2 millimeters. Yeah, the tube diameter is 25.4 millimeters. Here in the top left, you could see a picture, a real picture of the system. Well, in the inner part of the tube. And what I would like to say here is that two different kind of experiments were performed. One was the infrared lamp in order to characterize the axial heat transfer mechanisms. And for the radial heat transfer mechanisms, we heated the walls of the tube with an electric resistance. And also we use industrial scale data, also from the research group, to validate and to scale up the information. So for the fluid dynamics, we measure the pressure drop in the packet bed. Sorry. Yes. And with the Ergun equation, I mean, if we consider the Ergun equation as it is now, I mean, we consider the alpha and beta parameters that Ergun used in 1952, we could see that, well, please also look at the black symbols. We could see that the description of the pressure drop is not adequate. So we need to re-estimate these parameters alpha and beta to capture the inertial and viscous resistances in the pressure drop to describe the pressure drop that we have in our system. Now, with this information, we use it to calculate this K parameter, this permeability parameter from the packet bed. And now, with these K parameters, the only parameters to be estimated now is the effective viscosity. So for the effective viscosity, there was an issue, let's say, in literature, that most of the researchers consider, instead of effective viscosity, a fluid viscosity. And with this, an error occurs. This means that if you calculate the mass flux in these velocity profiles for the fluid viscosity, you would see that it's not the same mass flux as we have in the entrance of the packet bed. So we don't have conservation of mass. So what we did here is to estimate this parameter, but fitting the mass conservation. This means that if we calculate the mass flux in these velocity profiles, we will have the same mass flux as we have in the inlet of the packet bed. So here we estimate alpha and beta, and we estimate the effective viscosity. Now, for the radial heat transfer parameters. So a little bit of history. Most of the works consider a constant radial effective conductivity. This means that, for example, if we look here, the plot from the right, instead of having, look this dashed line, we have here a variation of the radial position of the radial effective conductivity. But instead of having this variation, we will have a constant value. Yeah. So let's say that it started at 0.2. So instead of having 0.2 increasing to 0.4 and then decreasing to 0, well, almost 0, we have a constant value. And because we have this constant value, we cannot describe properly, or we cannot capture with this parameter the heat transfer resistance in this coordinate, the radial coordinate, right? And also, most of the works also consider this wall heat transfer coefficient. Look here, this black HW set in the tube. I mean, in the boundary condition of the equation, set in the tube. However, they are missing some information in the inlet part of the tube, because they're considering this constant parameter. So what we did in this work was to consider this. Please again follow this right figure, this dashed line. So we can capture the heat transfer resistances here, mainly in the green part of the plot, which is the closest part to the wall and the one that has the highest temperature gradients. And with this, we can have some confidence on the HW parameter. So for the radial heat transfer results here, I'm showing the different radial effective conductivity at the different particle radials of the experiments and also for the evaluation. And we could see that it follows a similar trend, mainly in the core zone of the packet bed. And then as the radial effective conductivity approaches to the wall, it means the left part of the figure, it comes to almost 0.4. Yes. So if we have a low radial effective conductivity, it means that the heat transfer becomes lower and lower, and then the temperature gradient is increasing, and then we're capturing the temperature in this part. So translated this information to the simulations, we could see here the green lines and the red lines is the classical approach and the boundary layer approach, both used on papers in literature to describe temperature profiles. However, if you see the experimental data close to the wall, you can see that these approaches don't describe properly the temperatures. But if you see the blue lines, I mean the pseudo-local approach that we developed in this thesis, you could see that the description of the temperature in the wall zone is adequate in comparison with the other approaches. So if we translate this information in absence of reaction to a reactor model, we would see some difference with the different models. So, for example, if you look at the yellow lines, we'll see that this is a model considering plug flow and a constant parameter of the radial effective conductivity that describe or the results shows that the hotspot is formed at 1.5 meters and it has a value of 457 degrees. But if we look, for example, at the one that we developed in this thesis, you will see that there is a difference of almost 1 meter in our reactor of the prediction of the hotspot, and also the magnitude is lower than the one from the classical approach. So a significant effect has the heat transfer parameter has a significant effect on the prediction of hotspots. So here, the pseudo-local approach showed that could be the most reliable approach developed so far in literature to describe highly exothermic reactions in packet bed. But what about the impact of the actual effective conductivity? So, as I said before, if you look at this figure, this is a qualitative representation of the temperature profile in a reactor model where a highly exothermic reaction is occurring. And you could see that the lowest temperature is in the inlet, and then it's increasing because the reactor is heated, and then it reaches a maximum value of which is the hotspot, and then decreases, and then it has the same temperature at some length position in the reactor until the outlet of the reactor, right? So to characterize this effective conductivity, we did some experiments considering an infrared lamp, and then with a fiberglass jacket, this is an isolation material. We also ensure that we don't have any kind of radial temperature gradient. So with this information, following also this equation, we characterize the actual effective conductivity. And then the results are shown here. So you could see dashed lines, continuous lines are the dotted lines. So the continuous lines are those from this thesis. And I wanted to compare with the dashed lines, which is considering an actual effective conductivity from literature. from Botruba, which was the highest value that I found for an actual effective conductivity. And then the dotted lines is the actual effective conductivity developed by Yagi in 1960. So I would like to say that this correlation from Yagi is the most used in literature to describe the actual effective conductivity in packet beds. So as you can see in the figure from the right, the green line and the green dots is the one from this thesis. I mean, the dots are the experimental, well, estimation from experiments. And then you can see here the difference between the most used actual effective conductivity and the highest found in literature. So let's see if this has a significant impact on the description of a reactor. So some analyses were done. First, evaluating the effect of the particle Reynolds and also the temperature of the bath. Yeah, so at low bath temperature, 440 degrees, we could see, yeah, smooth prediction, well, difference between the different actual effective conductivities. I mean, here, for example, from Yagi, we have the prediction at 0.2 meters, while in this work is at 0.4 meters, so 20 centimeters. But if we increase, well, if we put harsher conditions on this reaction, we would see that considering Yagi's correlation, I mean, the most used correlation from literature, we could overpredict a hotspot or even a thermal runaway situation, while the actual effective conductivity developed in this work doesn't show this hotspot prediction or this thermal runaway. And if we consider the actual effective conductivity from Botruba, yeah, the temperature is even lower. So with this, I'm trying to show that, well, not trying, I'm showing that actual effective conductivity has a significant effect. I mean, now if we compare the feedstock composition, I mean, the amount of ethane, oxygen, mainly in this reactor, we will see that, yes, if we have more methane than oxygen, well, always more methane than oxygen, but if this ratio increases, yeah, we have this increment in temperature. But if we increase the oxygen, this means that the ratio between oxygen and ethane becomes closer. We also have another prediction of the hotspot becoming a thermal runaway situation, considering the most used actual effective conductivity. So with this, I would like to conclude that, well, first, a local approach was developed, yeah, and provides a better characterization in comparison with other approaches from literature, mainly for packet bed reactions with low two-particle emitter ratio. Also, some significant differences, as I show, exist between this local approach and the conventional approach, mainly in the hotspot position and the magnitude. And well, last conclusion, actual condition really matters. I mean, it's an important phenomenon that should be considered. Besides, the few works from literature says that, yeah, it's not important. Yeah, here in this thesis, we have proof that, yeah, it's something important, mainly because this parametric sensitivity. And also some perspectives is that this methodology, general methodology from pressure drop data to to develop the velocity profiles in a packet bed, and also the pseudo-local approach can be used for different reactions, mainly highly exothermic reactions, for process concept design, optimization, intensification. So this methodology is useful for other people that are working in exothermic reactions. Finally, I would like to say thank you to the C123 project for the funding received while I was in Ghent, in Belgium. Also to CONACYT, without the H, to provide the fellowship from this doctoral program. And last but not least, my colleagues, my peers from the laboratory of well, here in UAM Iztapalapa, and also all the people that I met in the LCT in Belgium, mainly the care group from Professor Thibaut. And yeah, from my side, this is all. Thank you. Right.
Okay, thank you very much, Mr. Romero.
Yes.
We are going to move to the
Round.
interrogation part of this exam.
Yeah.
We'll now begin with the interrogation of the candidate by the examination board, and therefore I'm going to kindly ask Professor Kai Olav Hendriksen from Technical University of Munich if he has any comments, questions to the candidate, please.
Yeah, thank you very much, Mr. Chairman. And of course, thank you very much, Alejandro, for presentation, for the nice overview of the results.
Yes,
And,
thank you.
Congratulations, of course, to your achievements. We have
Thanks.
seen publications which came out, and that's, of course, also very nice. And so you contributed to the scientific community, and now we will see what about the citations of these publications. So in the future, they will tell us how important the work will be.
Yes.
Yeah, we had already a private defense, and we discussed a lot of things. So, but of course, still I have some questions, if you allow me, Chairman.
Yes. Yeah.
Maybe for the broader audience, because I don't know how many people are sitting there, and maybe family, maybe
Yes.
research associates, friends, and whoever. When you go back to slide 7, 8, where you summarize the mechanism and you draw pictures there, yes.
Yes.
If you go maybe to just to the reactions, because you say steps, and then you call them reaction steps, etc. But actually, for me, OCM, so the oxidative conversion of methane, is one reaction.
Yeah.
Because
Yes.
if you ask me, well, what about the reaction steps there? What about the elementary reaction steps? Could you elaborate a little bit on that? So is it just one step, or because we have a heterogeneous catalyst, so I assume that there might be several steps?
Yeah, well, yeah, I know. Well, here steps. I wanted to say that each step is a different reaction. Yeah, maybe it's not the most adequate way to say it. But for example, in the case of the OCM, yes, I know that there are some kinetic models that describe with more detail what's happening with the OCM. So for this reaction, well, for the reaction network or this reaction model, we follow this simple kinetic model, this preliminary kinetic model, because, well, first we wanted to see if these, well, the catalyst and this OCOM reaction could work, could have some potential to be scale up or to yeah, so we can do more research on this. So that's why we keep it the simplest possible yeah, for the kinetic model. I'm not sure if that answers your
I think
question.
this is a well convenient approach also, because for chemical engineers, we just write down the major reactions, and then we just see how it follows and what might be the sensitive reactions, etc.
Yes.
If you look now to the reaction rates, I mean, they are also very simple.
Yes.
And maybe also reaction engineers, they would assume also reaction orders, so
Yes.
exponents for the pressures, etc. Why didn't you consider that?
Well, first, the number of data that I had from the experiments, yeah, I first wanted to have the simplest kinetic model. So that's why I consider first order for each reaction. And yes, yeah, I would say that that's the reason why I keep it in this way. I mean, in the case I could have more data, yeah, I can evaluate it. I can evaluate if the order of each reaction has a significant effect on the description of the experimental data.
Okay, because if you just tell us how many parameters, fitting parameters do you have?
Yeah,
if you look for all steps and the pre-exponential factors, activation energy. So
yeah, well, we're at the beginning 24 parameters. I mean, per reaction and activation energy, and also the pre-exponential factor. Yeah, and for experiments, I had different responses. Ethane, well, the molar flow of ethane, CO, CO2, all the compounds, and yeah, I also I know that if I have more parameters, it becomes more. How can I say? Yeah, more difficult to estimate those parameters. So as a preliminary part of the work was just to starting with a simple kinetic model. But of course, yeah, I would like to, if it's not me, someone else to continue with this OCOM reaction just to improve the kinetic model.
Yeah, and if you would include now the exponents, etc.,
Yes.
then of course you will increase then the number of parameters for fitting.
Yeah, and also, well, considering the absorption with, I don't know, Langmuir, Hinchelwood, or Ellie Riddle, yeah, increasing the robustness of the kinetic model.
I know that you are not so familiar with the kinetic data for this. I remember from the private defense, I think, or please correct me if I'm wrong.
Yeah,
but
yeah, this kinetic data was obtained
yeah,
in the research group from Professor Thibaut, yes, by other colleague, and yeah, well, I'm familiar with the how it was, well, how the data was obtained, and also yeah, the operating conditions and everything, but I did not
sure.
physically make the experiment.
Please let me allow maybe one last question, because
Yes.
for reaction kinetics is always important that if you write down the reaction rates, like here, that we are talking about microkinetics. So actually, we neglect the mass and the heat transfer when we are evaluating the kinetics. So
Yes.
how sure are you that the Thibaut group gave you the right kinetics?
Yes. Well, the experiments were performed under some conditions to avoid mass heat transfer limitations, and also in a plug-plug regime. So this kinetic data, well, I can trust on the kinetic data, even to if I could have more data as experiments were performed, yeah, to use it in a more detailed kinetic model development.
Mm-hmm. And yes, how sure are you when you go now to the process modeling and you take now the reactions, the reaction rates? How sure are you that maybe heat and mass transfer is interacting? So because I remember that you said for your conclusion slide that it has been an isothermal model.
Yes, I know this is a preliminary model. I mean, and probably, yeah, the description of the process could be a little bit different, but yeah, what can I say? I try to keep it to keep the same trends, say the trends of methane conversion or the trends of carbon species yields. Just extrapolate a little bit the operating conditions to follow the trends. It's more like a qualitative description, but yeah, the work done here was to prove if OCOM could work, and based on this kinetic model, I mean, which, as I say again, maybe will change in the future, and it's not the ultimate kinetic model for OCOM. Yes, but at least give some hints of what could happen if we consider this C123 process with an OCOM reactor. So
Okay.
I wouldn't scale up immediately this process, but at least I'm showing, okay, yeah, could work. And this, well, in the conclusions, yeah, in the conclusions, I said that opportunity areas, oh, sorry, it's a little bit slow. Yeah, opportunity areas, well, some technical
Just
issues.
to have
Yeah,
a
well,
better model. No,
yeah,
to
yeah,
improve
opportunity
the
areas for the
model.
research for the kinetic model. Yes, and yeah, it's also something to consider the effect of the heat transfer and mass transfer, as I did in the ODH reactor.
If you go one slide back, I have one more question,
Yes.
which
Oh, sorry,
for the process modeling.
I have some technical issues.
That's
Sorry.
slide 9. No, 10. Excuse me.
10.
10.
Okay.
Because for the recycle gas,
Yes.
you mentioned methane.
Yes, for
You
the
want to go to the
recycling.
presentation mode, or you
Yeah,
just
yeah,
want to?
sorry.
Yeah.
Yeah, here. Yeah, for the recycling gas. Yes, sorry, I
It's
didn't hear the question.
methane and it's CO2. But as far as I understand, is that you produce also CO. So what happened
Yes.
with the CO?
Yeah, for the CO. Yeah, for the CO. Yeah, it is produced from the OCOM reactor as well as ethylene, and then ethylene and CO goes to the other formulation reactor. I mean, I didn't make any simulation or experiments for the formulation reactor. That was part of the project, but from other colleague in the group.
Mhm.
And yeah, the results in the other formulation reactor shows that all the ethylene and CO can be considered as totally converted. I mean,
Okay.
yeah,
Okay.
there is
So
no.
the HF reactor converts the CO, and
Yes.
so there's no CO left.
Yeah, exactly. The only compounds that are recycled are methane and CO2. Well, that's the goal from this process at the end. Yeah.
Yes. And how much CO2 is recycled? I mean, it depends on the conditions, of course,
feedstock.
but just a rough
Yes.
estimate.
Yes, well, something that I find good from this catalyst, the manganese tungsten cerium catalyst supported on silica, is that the production of CO2 is really low. I mean, I think that's also a feature from this catalyst. So the CO2 that we are considering in the recycling, most of the CO2 is the one that is contained in the feedstock. I mean, if we have shale gas, 7% of the total molar flow will be recycled again and again and again. So that's why we need a purge in the system, well, in the process.
Yeah. As usual in big plants, we have purge
Yeah.
flows.
Yeah, and that's something also that I mentioned in the opportunity areas. Maybe we can add some operation units to mitigate or to harness some reaction to react the CO2. Yeah.
If the chairman allows me, I have one more question, but to the other topic.
Yes.
Okay.
You're confident.
Sure. If you go to slide 19, there's
Yes.
For chemical engineers, a simple fluid mechanic formula, but for
yes.
non-specialists, maybe you have to explain this. Yeah.
Yes.
So what are the contributions for that?
Oh, sorry.
So
Oh,
the dt
yeah,
by
sorry.
dt, partial t, partial t.
Okay, so the formula, the first
Yeah.
term, the accumulative term that describe how the temperature is increasing or decreasing on time. Yes, this rho v is the density of the bed, the Cp, the specific heat of the solid. Yeah, the second term, the convective term that consider how the movement of the fluid, I mean the velocity of the fluid, affects the temperature, and the term from the right of the equal sign, the axial effective conductivity term. Yes. So
accumulation,
the
transportation,
the accumulation convective term and the conductive term. Yes.
And it's a time-dependent equation. Why is it time-dependent? If you have a constant flow and you just take a picture after hours or days, I mean, there are only two possibilities. The reactor is still working or the reactor is gone. Because the temperature is so high that it's the steel is melted and the reactor is gone. So why do you need a time-dependent temperature influence or heat?
Well, this is something I didn't show in the thesis, but I would like to study and to understand these transients, the transients profile of the temperatures. Well, as I said before, it's not part of the thesis, and the results showed here are only the at the steady state. But another issue found in literature is that most of the time the simulation describes, for example, the performance of a reactor in 1 minute or in 30 seconds. So really fast, faster than we could expect from real life. So I would say that the accumulative term, it means this density and the specific heat, has something more to tell us. Or this, I mean, because if we add some parameter here, we could see some delay on the description of temperature on time. However, we will always reach the same steady state. So that's why I use this model. That was the reason.
And the figures below there for the temperature, for the heat conductivity and for the temperature, this is after steady state, reaching the steady state.
Yeah, this is steady state. Yeah, these experiments were performed, well, in absence of reaction, and the steady states, well, the lowest particle Reynolds reaches steady states at, well, like 1 hour, 50 minutes, and the highest particle Reynolds, in 10 minutes, 5 minutes. Yeah.
And if you go, and then I'm done. If you go one slide further to 20,
yes,
then what we see is the steep increase there. It really goes to 200, because I was always thinking when I also read your the paper and the thesis, well, it starts really at 200 degrees centigrade, but it must, because they have different slopes. If you look at the slopes of each of these curves, they have different slopes. So they really start at the same temperature. I was just wondering. Yes.
Well, just for let's say plot purposes, but all the data started at, well, it starts at 200 degrees, and then, well, the slope is mainly because the prediction of the hotspot. So
yes, because it changes the actual position.
Yeah, exactly.
Yeah. Okay.
Okay.
Thank you very much. I'm
thank you,
done.
Professor.
I'm finished. Yeah. Thank you.
Thanks.
Thank you, Mr. Hendrickson. I will now ask Mr. Gamaliel Galicia if he could participate with his questions or comments.
Okay. Can you hear me?
Yes.
Okay. Thank you, Professor Richard, for the time. And thank you very much, Alejandro, for the presentation. Congratulations for the hard work. It's a very difficult work that you work with two reactions. And also, I would like to congratulate your directors, Professor Joris and Professor Carlos. Congratulations. I have several questions regarding your thesis. I'm going to start from the catalyst to the process.
Yes.
Did you use two different catalysts, very complex catalysts from my perspective?
Yes.
The first one is based on magnesium, I think, sodium tungsten, and silicon dioxide. Do you have and the other one is based on, I think, is molybdenum, vanadium, niobium, and tellurium.
Yes.
And with titanium dioxide. So do you have any idea of what is the role of each metal in each reaction?
Oh, that's a good question. Not exactly. Yeah. Well, what I could say here is that, well, for example, for manganese, tungsten, sodium catalyst, I saw different performances, but was because the support is here silica, and I also saw the performance when the support was alumina. So I'm not sure. Yeah, wait, sorry. Which part of which metal has an effect on the, I don't know, selectivity to a specific component like ethylene or some. Yeah, I'm not sure about the role of the metals of each catalyst.
Okay, because well, my question is, what is the role of the support? For instance, for this for silica, the
Yes.
silica takes. Do you think that takes part in the reaction? The silica.
Could be because, well, the other catalyst that I saw, the one supported in alumina, the performance of the reaction was that the CO2 selectivity was the highest among the other carbon species. So basically, that was a discussion we had with the other colleagues in the project. And that was the reason why we selected this catalyst, the silica supported. So yeah, I mean, I didn't make any work towards understanding the role of the support, but I could say that yes, it could have a significant effect or is participating in the reaction.
Okay.
Because it's the same catalyst. It's magnesium, tungsten, sodium, but the support changes. So I could expect that support has an effect.
Okay, thank you. In this slide, you present different reactions.
Yes.
And the operational conditions are about 800 Celsius degrees.
850.
Am I right?
Yes.
850 Celsius degrees. My question is, how you can be sure that all that reaction that you present in this table are heterogeneous reactions, or because the reaction temperature it can occur very, I think, at least 3 reactions in homogeneous phases.
Yes.
So what do you think about it?
Well, considering not this catalyst but other catalysts, yeah, I have seen also some works in literature for well, mainly for OCM, that considering two paths, the heterogeneous path and the homogeneous path. So it's a little bit complicated to say which reaction is occurring in the gas phase and the other in the surface of the catalyst. Yeah, because yeah, the radicals of CH3, yeah, it's a little bit complicated. I cannot be sure from these experiments what is occurring in an heterogeneous way or in an homogeneous way. What I can, let's say, suggest for the experimental team is that repeat the experiments in absence of catalyst and then experiments with catalyst. What also would be a little bit difficult to understand, for example, the role of ethane, because ethane is produced. I mean, if we have a feedstock only with methane, ethane is produced, but then ethane could react on the, well, following an homogeneous way or a heterogeneous way. So yeah, in this kinetic model, I consider that all the reactions but the thermal elimination of ethane are occurring because the catalyst.
Okay, just be careful with that. Maybe you can take part of homogeneous reaction.
Yes.
So, okay. In table 2.3, that when you describe the activation and that one.
Yes.
Why do you think that the total and partial oxidation of methane is minor than the oxidative coupling of methane, if their selectivities are present the opposite behavior? What do you think that?
Sorry, which reaction?
The partial oxidations.
The partial oxidations. Okay.
And the
in
total oxidations, yeah. And the total oxidation is the POM, and the other one, TOE and POET, please.
Yeah. So yeah, total oxidation of ethane, the partial oxidation of ethylene, and so these two reactions.
Partial oxidation of ethane.
So the partial oxidation of ethane is the one, we neglected from the reaction network, because we saw that it didn't have a significant effect and it was not statistically significant. So for the TOE, total oxidation of ethane, and partial oxidation of ethylene, in this case, sorry, the question was towards the explanation.
Why the activation of energy are minor than the OCM reaction?
Minor than the OCM reaction. Well,
for example, the POM reaction is 129, and the OCM is 227.
Yeah. Yes. I think. I could say that it's because the reactivity of methane and the reactivity of ethane. I mean, the energy needed to break the bonds of carbon hydrogen for methane is higher than the energy needed for the ethane, well, the carbon hydrogen bonds. So this could be something, this information could be something to explain to the amount of the activation energy for the OCM and the total oxidation of ethane or the partial oxidation of ethylene.
Okay, thank you. Well, I have another question. Regarding the temperature of this reaction system, how sure are you that coke is not formed?
In which
because
system?
it's in the oxidative couple of methane reaction. How sure are you? Yes. How sure are you that coke is not formed? Because
no. Well,
because the temperature is high. It's quite high. So maybe you can get the coke.
We can, but at least from the experimental procedure that another colleague from the lab did, he didn't see any coke formation at these operating conditions. And
How they didn't see it?
how they because the presence of oxygen that is oxidating the carbon species. I mean, if we goes in a situation where we don't have oxygen, maybe we could have some coke formation.
Okay, well, maybe with carbon balance. That did you realize carbon balance?
Yes, carbon balance were yeah, about 95, 96%. So
Okay.
Mhm.
Okay, well, let's go to the other reaction. When you
which fraction?
the second reaction, the ODH, please.
Ah,
In the slide, well, first the slide 10, please. The slide 10.
Slide 10.
The slide number 10, please.
Yeah. Just a question. You're seeing the presentation screen or the screen from the other point of view? I'm just
The presentation screen, yes.
yeah.
That's correct. The 10, the number 10.
Okay, perfect. Yeah. Mhm. Yes.
For you, what it doesn't mean real simulation? Why
yeah.
real?
Yeah. That's something that I had to correct on the thesis, because first I consider real feedstock, and then a suggestion
Okay.
from one of the jury members was, no, it's a real simulation feedstock. This is because, well, I'm not taking real feedstock from a well or something. No, I'm using data from these wells. For example, natural gas, considering methane, shale gas, methane, ethane, and CO2, and biogas, methane, and CO2. And also something that I should mention is that no contaminants were considered in this simulation. So I'm just taking the composition that we could expect, considering only the carbon species that we evaluated in the kinetic model, to have the simulations of the C123 process. Yes.
Okay. I have a question that we made in the private defense.
Yes.
Why you didn't use the pseudo-local approach in the simulation for this reaction?
Yeah. Well.
Why?
Yeah. I could say two things here. One was the goal from each part of the thesis. Here for OCOM, as I said, it was like well, a TRL 3, 4. So that means that the technology development, the technology of this processor system was not so developed as the one for the ODH. Just now is industrialized and this not. So for this, we wanted to see first with a preliminary kinetic model if OCOM could work. So that was part of the goals of the thesis. I mean, I didn't have time to explore more on, I don't know, to develop a more robust kinetic model and also to couple this to the ODH reactor. So that's one thing I could say. The second is the operating conditions, because the characterization of the transfer phenomena for the ODH were done at the operating conditions for the ODH. This means 400, 500 degrees, up to 600 degrees, and also the pressure drop. Yeah, the shape of the catalyst. Yeah, I mean, there are a lot of factors and variables that we need to consider to use on the ODH. And for the OCOM part, yeah, this is a catalyst that I'm not sure how would be the effect of silica on the heat transfer. I mean, I can use correlations from literature, but yeah, that wouldn't be the same work that I did in the pseudo-local approach.
Okay. What kind of shape of the catalyst did you use in the OCOM reactor?
In the OCOM was powder.
Powder. for a industrial reactor?
No,
For-
not for industrial reactor. For here, I just consider this ideal Occam reactor, isothermal reactor. Yeah, but for for the industry.
What is this? What is the size of the Occam reactor that you present here in this simulation? What is the size of the reactor?
Size is not so much. It's just at 30 centimeters. So it's just considering idle reactor, considering operating conditions similar to those obtained in the lab. And as I say, for
the length of the reactor.
For the length of the reactor, I mean, industrially speaking, should be 2-3 meters or 10 meters. Yes, but for the simulations, I didn't consider a large length. I just considered 30 centimeters for the simulations. I would say that the critical parameter for the simulations was to keep the same space-time. I mean, the amount of catalyst per the molar flow of methane. That was the variable of the operating condition that I consider that would be similar to the industrial scale.
Okay, just be careful with the size of the reactor and the size of the particle, the catalyst particle that you use. Regarding to the ODH process or the ODH reaction,
yes.
Did you present? Did you mention that all? Let me see. That mass conservation was achieved in the pseudo-local approach in comparison with the bond layer approach and classical approach. That's right?
Yes, that's right.
Yeah. Okay. And why do you think that occurs?
Well, first, I would like to say that, well, maybe the next slides. Here. Sorry, please. So, the yellow lines, the classical approach from literature. This approach considers log flow. It means same velocity in each radial position, and also a constant parameter. And if we, also from the same literature, if the researchers considering instead of log flow fluid dynamics, they will see a decrease in the hotspot prediction magnitude. I mean, from 457 to 452, but they are the actual position prediction. I mean, almost 1 meter and then 1.5 meters. So this is only considering hydrodynamics, and then considering the effect of the pseudo-local radial effective conductivity or a constant radial effective conductivity. So that's why it has a significant effect. And also, in this literature, the hydrodynamics was developed considering a non-conservative model. So I'm comparing here, for example, these black dashed lines with a conservative model. So that is the effect that considering an effective viscosity that follow the mass criteria conservation has on the prediction of a reactor model.
Okay, I have another question.
Yes.
Those particle Reynolds that did you use are in laminar or turbulent regime?
Well, 1,400 and 1,050, will be turbulent. I know. And 700, because the configuration of the packet bed, I would say turbulent effect is something that we should consider on fluid dynamics.
Okay, my question is going related to that because the fluid dynamics that you use to describe these heat transfer parameters or heat transfer experiments was based on Navier-Stokes Darcy-Forchheimer. That's right.
That's right.
Okay. Why you didn't use a turbulence model? Please explain. If the particle radius is in turbulence regimen.
Yes, that's a good question. Well, first, yeah, the first thing I saw when I was doing fluid dynamics was the mass conservation criteria that in literature is not so common to find effective viscosity for this kind of system. So I focused all my work, my duties on this Navier-Stokes-Darcy-Forchheimer. I didn't go in the direction of the turbulence model because I was focused on the let's say the pseudo-local approach. So my efforts were towards the heat transfer. I didn't focus on the turbulence model. Yeah, I mean that's my honest question. I didn't have time to focus on the turbulence model.
Okay. Regarding the regression of the heat transfer parameters,
Yes.
I couldn't see the statistics
Yeah.
from those regressions on that different approaches.
Yes.
Do you have any to show me or to show us?
Not in the slides, but I'm sure that on the thesis I show the confidence intervals and also the F value. And not sure if the degrees of freedom, but what I can say here is that I didn't see any.
Because you mentioned that the pseudo-local approach is the best to describe the experiments.
Yes.
But I only can see this on the graphs, on this graph, not in the statistics of the parameters and the regressions.
Yeah. Well,
I would like to see it. But if you don't have in the hand, don't worry.
No. Well, also was difficult to show like a coefficient like R square coefficient or factor to describe how well is the description between one approach and the other. Yeah, I don't have that information. Sorry.
Okay, don't worry. Two more questions, if the chairman's allowed me. Yeah. From my experience, the description of the void fractions, have a high impact on the velocity profiles, and then the velocity profiles have a huge impact in the heat transfer when you estimate heat transfer parameters.
Yes.
Do you agree? Okay.
Yeah, yes.
Why you use a declared equation to describe void fractions, and why you didn't use another correlation that could be more, how can I say, more accurate?
Well, I found that the correct correlation was one of the most adequate correlation from literature to describe this kind of systems. This means packet bed with a low to-particle diameter ratio. I mean, the work from this researcher was done in a range of, I mean, I'm roughly speaking, sub-diameter to-particle diameter ratio between 2, 3 till 12, 15. Don't remember exactly, but yeah, this researcher validated this correlation at several to-particle diameter ratios. So I consider that enough to use it to describe the void fraction in my system.
Okay. And my last questions, when you predict the hotspots,
yes.
Can you put the slide when you put different hotspots with different approximations? please.
Yeah, this one.
That one, yes.
Yes.
Well, the layer approximation and the pseudo-local approximations, for me, is quite the same.
Uh,
What about the concentration profiles or the conversion and the selectivity in the reactor? Do you have any graph that could show us the behavior of conversion of selectivity
yes.
with that both approximations?
Yes.
Maybe it's very similar or it's very different.
Yeah,
I would
don't
like
have,
to see that.
Yeah, I don't have the slides now, but on the appendixes from thesis, I showed the different profiles for the conversions, selectivities, comparing boundary layer approach, local approach, and classical approach. What I could say is that it has similar trends. I mean, if the difference between boundary layer approach and the local approach is narrow, the selectivity and conversion is also narrow. It follows a similar difference.
Okay, well, it's all for my part. Congratulations again.
Thank you.
Very high quality work.
Thanks.
Thank you, Mr. Professor Galicia. Now I'm going to ask, please, if Professor Max Say from Kent University could connect online and present his comments.
Yes.
Oh.
Can everyone hear me?
Yes.
Yes, Professor, a little bit low.
Okay.
Yeah, done.
Yeah, okay. So first of all, congratulations on your work. I mean,
Thank you.
it's almost 2 theses, 2 topics.
Yes.
I think it would have been nice to combine them on the same reaction system, but that's a discussion we had last time. So
Yeah.
It is what it is. I have a few small questions to test how much you know about each of the topics. So the first one is about the catalyst for the Occam reaction.
Yes.
It's quite a complex catalyst.
Yes.
Do you have any idea how it is made?
How what? Sorry?
How it is prepared?
Yeah. Well, it's with impregnation. Actually, I have a slide here. Okay, I think I don't have a slide of yeah, synthesis method. Yeah, well, this is the method. I mean, I don't really know letter by letter, but it's a sequential impregnation of yeah, manganese and sodium tungsten. I mean, the precursors are manganese nitrate tetrahydrate and sodium tungsten dihydrate. Yes, I mean, the preparation is not so complex as the catalyst, the multimetallic catalyst that I use for the ODH. But yeah.
Well, the other is a co-precipitation. I was wondering whether it's an impregnation or a co-precipitation for the silica.
Yeah.
The use of the term support for silica is not completely correct for this catalyst. So silica really plays an active role in the reaction.
Yes, that's yeah.
So I'm not surprised that if you change to alumina, you see completely different things. The silica is absolutely not inert, and the sodium that you add plays a key role in stabilizing certain silica phases.
Yes. Okay.
Yeah. Then a lot has been said about details already, but I want to hear your thoughts about the potential of this Occam process. So maybe go to the slides.
Yeah, this one.
Yes. So on paper it looks interesting, but there are quite a number of caveats, and I would like to hear your comments on which things should be improved, where are uncertainties, what would you work on?
Yes, well, for sure, there is space for a lot of improvements. Yeah, well, I would say the most obvious is the kinetic model. But for to validate a kinetic model, more robust kinetic model, we need experimental data. So what I could suggest is to expand this experimental data, preferably on trying to understand the role of co-feeding ethane, co-feeding ethane, methane in this catalyst. Yeah, also expand the range of the operating conditions from the experiments that were performed. I mean, space-time, oxygen to methane to oxygen, inlet molar ratio. So with this information, we can start developing a more robust kinetic model, and then
Yes,
consider
because you do a simulation under conditions that are extremely different from the experimental conditions.
Yes.
Using a power law kinetic model.
Yes.
I would be very afraid of that.
Yes. Well, I know extrapolating this model is not the best way to follow for to scaling up lab information to industrial scale. I follow trends. I follow qualitative performance of carbon conversion, carbon yields. I mean, I wanted to see what could happen if the trend still goes. I mean, probably I will show a slide to explain a little bit better. This one, for example. For example, the effect of space-time. This is something I didn't show in the slides. It's a backup slide. Here, I try to understand what is the effect of increasing the space-time. This means we increase the amount of catalyst per flow of methane. So I'm just following trends, and I'm just following like, okay, if we increase the space-time, we could have a total conversion of, well, further conversion because ethane is produced first and then is converted to produce ethylene. And what could happen if we increase the space-time? And I did the same exercise with what would happen if we increase methane to oxygen ratio. So I'm pretty sure of the operating conditions where the experiments were done, but I'm also following the trends, comparing with what I found in literature. Not going very, very to the extreme, to, I don't know, 100 kilograms of catalyst per second mole, but keeping in a range where we can use on the industry and where we can extrapolate a little bit more if we could have a more confident kinetic model.
Have they tried experiments for these very high methane oxygen ratios?
Not for this catalyst. No, I mean, no, that's something we need to do.
I would expect a lot of coke formation.
Coke. Yes.
You consume all your oxygen.
Yeah, exactly. Yeah, because all the oxygen was gone. But as I said, I mean, an experimental campaign could be proposed. Also, trying to keep this amount of oxygen conversion not to 100% to avoid coke formation, but that's some work that should be done to propose the more adequate experiments.
Yeah. What are shortcomings in the process?
the shortcomings. But so what do you mean with shortcomings? Like
Well, I mean, this is a process scheme. If you had $1 million to invest, where would you put that $1 million?
I wouldn't put the $1 million directly to the process, to scaling of the process now. I would put the $1 million to more research on kinetic model, on experimental data, on yeah, all the perspectives that I mentioned from this OCOM, well, the C123 process, the OCOM reactor.
But what I'm aiming at is there are several problems. You have reactor design and
Yes.
heat transfer. You have
Yes.
catalyst design. You have kinetic conditions. You have what to do with the recycle stream. You have the hydroformylation reactor. You have the separation. I mean, where do you see the biggest obstacles?
The biggest obstacles, as it is now, I would say, yeah, the separation of methane and CO2. I mean, at some part we need to purge CO2, and that costs money. And well, also we don't want to purge methane because the greenhouse effect that has methane is higher even than CO2. So as it is now, I could suggest to improve that area, because OCOM, the product from OCOM, mainly ethylene and CO, will react in the hydroformylation reactor. So we don't need to take care of ethylene and CO after the hydroformylation reactor. But the issue is methane and CO2.
I'm surprised you think you have full conversion in hydroformylation, but that was not your topic, right?
And yeah, not my topic, but I talk with my colleagues working on the formulation reactor, and they reach almost 100% of conversion of ethylene and CO.
Okay. Yeah, depends on the catalyst, I guess, but for the homogeneous rhodium catalyst, that's not really the case.
Okay.
And then the second topic, again, you build an advanced model to describe heat transfer more accurately, and then you use that model to describe a chemical reaction.
Yes.
And the position of the hotspot.
Yes.
Again, from a modeling point of view, this is quite a big step. You have one reactor with a particular packing. You heat it with the infrared lamp from the top. You measure the actual temperatures,
Yes.
which are quite low.
Yes.
And then you use that model to describe a very exothermic reaction in a packed bed reactor.
Yes.
So same question, what do you trust that model? Why do you trust that? And which additional measurements, experiments would you do to
well, yes.
increase that trust?
Yes. Yeah, to answer that question, I would say it should be answered in different parts. For example, for the radial heat transfer, I could say that I trust the model because the experiments, yeah, here, the experiments were.
So just to help me, the middle slide, it should be radial position as well, right?
Sorry.
The dimensionless radial position, it should be in the middle figure.
There is a typo here. Yeah. Sorry. Yeah. So yes. Yeah, for the radial heat transfer. So here, this experimental data was obtained also in the research group for the industrial scale, the pilot plant scale reactor. So it has temperatures similar to those that we could see in the industrial process. And this model, the local model, described properly the temperature in the closest zone, to the wall, which is the wall zone. So For the pseudo-local approach, yeah, I can trust this approach. And if I compare the approach with other approaches from literature, I would see many difference in magnitude and also position of hotspot. That's something for the radial effective conduct, well, radial heat transfer. For the axial impact, here I know, yes, is the temperatures are lower than those for the radial. To be honest, it's difficult to obtain experimental data well, having no radial heat transfer. That's why we consider a fiberglass jacket in the surrounding the tube and heating the system with an infrared lamp. So it is difficult to have a source of heat to heat the tube and to generate these 500 degrees or yeah, this temperature gradient of 500 degrees, 200 degrees. So what I could say here is that the correlations developed from literature, as I show in the figure from right, the most used, the one from Yagi, the blue one, and the Votruba, which is the correlation with the highest value of the actual effective conductivity that I found on literature, could give us, yeah, some idea that at least in this range, we could have the actual effective conductivity, even if the experiments or the validation of these correlations were done at temperatures lower than the radial temperatures, which are, well, in this case, 100 degrees, 80 degrees, 60 degrees. So also some suggestion for future work is to improve this experimental data to increase the temperature gradient in the axial direction and see if there is a significant effect between the results obtained in this thesis and the result that we can obtain if we increase the temperature in the actual temperature gradients. So I cannot entirely trust the actual effective conductivity, but at least comparing these the correlations, I would say that my correlation is between those reported in literature and that the effect of the actual effective conductivity is significant, even if, yeah, even the temperature data that we have for the actual experiments.
Okay. Would be nice if you could think of radically different experiments that could be done to support, right?
Yeah,
so you only suggest a little bit more of the same, but could you think a bit out of the box of experiments you could do to validate your model?
Yeah, yes. I've been doing research on different axial heat transfer experiments, but I haven't found some proper experiments for the axial heat transfer characterization. But as you mentioned, need to think out of the box. Now I cannot think on some idea for these experiments.
Okay.
Yeah.
Thank you. That's all.
Yeah, thank you, Professor.
Thank you, Professor Marseille, for your interesting comments. Now, I will kindly ask Professor Héctor Fernando Puebla from Metropolitan Autonomous University to participate in these questions.
Okay, thank you. Hello, good morning to those in Mexico City, and good morning to those in Europe. I want first to thank Omar and Alejandro for the invitation to participate in this PhD evaluation. Hi, Alejandro, again.
Hello, Professor.
First, thank you for your detailed response to the revisions and comments raised during the first stage of this joint PhD program. Since my concerns were addressed in that evaluation, I have just a few additional comments and questions to clarify your doctoral scope, limitation, and perspectives.
Yes.
First, regarding the motivation behind your doctoral research, to explore improvements in two processes for methane-ethane valorization. And considering the renewed interest in and potential application of biotechnological processes,
Yes.
could you provide some comments on the use of bacteria for methane and ethane conversion as potential competing technologies to the process you are studying?
Sorry, could you repeat the question? I didn't follow it.
If you have some comments about the use of as an alternative to your approach of the use of biotechnological processes.
Biotechnological processes, but that could apply for, well, let's say OCOM was focused on valorization of methane, and the work developed for the ODH is like a general methodology following pressure drop, heat transfer, characterization that we could use in packet beds. So I would say for biotechnological processes, yeah, the methodology developed. I would say this slide could help. Yeah, this slide. So if we imagine instead of having a reactor performance to predict hotspot prediction, yeah, I know for biotechnology applications, the goal or the focus of the research is different. But yeah, I could suggest to follow, yeah, in order to characterize fluid dynamics, pressure drop data, the characterization of the parameters alpha, beta from ergon, and for the temperature gradients, also the pseudo-local approach. I'm not familiar if the impact of describing these temperature gradients in the wall zone is something important or no in the biotechnological approaches or processes.
Oh, okay, I think that probably my question was bad understanding or formulated. I only want to hear some comments about the possibility of the use of biotechnological processes for methane reduction compared with the sorry for the confusion.
Yeah, well, I'm not really familiar again with biotechnological processes.
Okay, no problem. Okay, no problem. Only was a motivation about that possibility, but no problem.
Yeah.
Okay. My second comment pertains to the ODE case. Specifically, you refer to compute two critical parameters for describe with more precision the heat transfer in the reactor. Have you considered alternatives to your proposed method for estimating these parameters? In particular, I believe that sub-methodologies from control theory could be useful here and might even be more practical, such as parameter estimation using state observers, which uses a base model of the process that you have and available measurement to estimate model parameters.
Yes.
So, yeah.
Yes, but I mean, for those models or the methodology that you mentioned, those models follow, how do I say, for example, a similar shape of this equation, like a cumulative term, convective term, because for control and optimization, sometimes simpler models that that don't capture the effect of, in this case, heat transfer mechanisms are not really used. It's more like a simple model that can be adjusted depending of the variables of the operating conditions. And I'm not really sure how these variables or parameters are estimated or controlled. I didn't make use of those methodologies for the estimation of these parameters.
Okay, no problem. It's okay. Okay. My next question concerns using more recent alternative approaches to evaluate the parametric sensitivity, hard stops, and thermal runaways in the OED case.
Okay.
I believe that some results developed by the Bickel's group could be useful in this context.
Yes.
Yeah.
Yeah. So,
okay, the question is if you know that approaches. It's I saw them in a paper in the 2021. Probably it's a recent paper.
yes. But sorry, I didn't follow the question. Could you repeat it?
If you have considered the use or as an alternative approach to evaluate the hot spots and thermal runaways using that approaches, more recent approaches, because you in your
Oh,
thesis
yeah.
you use some old approaches. Do that?
Yeah, I didn't follow those other approaches. I just used the conventional and conventional approaches, classical approach, ponderal approach. What I did was just compare those approaches from literature with the one I developed from this thesis. Didn't have the opportunity to look at the other approaches you mentioned.
Okay, it's okay. Okay, your doctoral research incorporates various methodologies from
Yes.
process engineering to enhance the understanding and operation of complex processes through detailed modeling approaches. Now, given your expertise and the tools you utilized in both case studies in your PhD thesis,
Yes.
which research lines do you intend to pursue in the coming years?
Well, for sure, chemical reactors engineering, chemical reactions engineering. I think that from this thesis, I'm taking some nice tools and fundamentals on transfer phenomena. Also, the research done in Belgium from the kinetics incorporated into processes. I'm not really sure which line I will follow, but I know that based on the fundamentals and that I taken from the PhD, I could choose options on biotechnology or oil gas research, or mainly those two topics.
Okay. Thanks again, Alejandro, for your responses, for your work, and I don't have any additional questions or comments. Thank you.
Thank you, Professor.
Thank you, Professor Hector Puebla. Well, I have a couple of questions that I would like to ask you, if you please. You have determined some use the pseudo-local radiate effective thermal conductivity as well as the actual thermal conductivity to model your reactor.
Yes.
And but first you determine a correlation for the actual conductivity.
Yes.
It says
this one.
This is the results. It's similar to that of Jackie and co-workers in the farm.
Well, yeah, it has same structure. Let's say the parameter that described the terrain, let's say, is different. But yeah, it's something similar than Ergun, because with Ergun, okay, I follow the same structure, but the parameters are those that will make the values of, in this case, pressure drop could be a little bit up or down. So the same for the
You have two terms in that correlation.
In Ergun equations, yes, but for example, in the axial effective conductivity, I only have the axial effective conductivity term. It's the only one.
Well, in equation 3, 326 in UTC.
In which equation?
326.
326. Could you
Yes,
elaborate?
there is a first term for the effective conductivity, the actual conductivity divided by the conductivity of the fluid is equal to the conductivity without air that you determine.
Yeah, in the correlation. Yeah. It's in the
yes,
correlation.
I'm talking about the correlation.
Yeah. Okay.
Okay, which is similar to that of Jaggis.
Yeah. Exactly.
Well, that's what I was pointing out. You decided to use this for any reason?
Yes. Well, because the experimental estimation, the estimation of the effective conductivity based on experiments showed this trend. So based on the trend, I selected the shape of the equation and then I just estimated the parameter to have the description to fit the experimental axial effective conductivity.
Well, there is evidently a lot of difference between your results, the experimental, and the predictions of the other correlations.
Yes.
Did you come across thinking, well, what's happening here? Is it that the experimental data that they use and that you are using is so different? Is it that the correlations are missing in some kind of information?
Yes,
How do you explain?
So something that I probably, just for the time's sake of the presentation, I didn't mention was that these correlations, all the correlations presented here were obtained at very different conditions. Most of them at particle Reynolds lower than 100. Yeah, the only one that I found up to 1,000 particle Reynolds was the one from Botruba, the red one, and just curious that is the one with the highest value of the axial effective conductivity. So that gave me an idea that maybe axial effective conductivity could have an impact on the description of the temperature profiles in absence of reaction and under kinetic conditions. So that was also one of the starting points of my research, and then that's why I decided to do also the experiments and to characterize this parameter and then do simulations. So it was kind of the motivation of this work, the comparison with the work from Botruba.
Are there any correlations? The equipment that you use, you mentioned that it has been used before.
The one from Yagi or which one?
No, the one from the group that you use for determining the
axial effective conductivity.
The equipment that you use.
This one the equipment. Yeah. Okay, yeah.
Are there any correlations from those works with the same?
Yes, but the conditions were not so high as the one I
higher Reynolds, remember?
The particle Reynolds, yes, because the particle Reynolds, if I remember, were up to 630 or 500 something. So it was something like here. So I decided to go a little bit more with the particle Reynolds and to reach the particle Reynolds above 1,400. That's why this experimental data was the one I obtained during the thesis, and the experimental data obtained in the research group many years ago were obtained in this range.
Yeah, right. I noticed that for Botruba calculations,
yes,
you used some properties. You needed some properties of the particles to calculate three constants.
For the constants, the constants, for Botruba were obtained based on different shapes, materials, and other variables.
But you had to use glass properties instead of the properties of your catalyst.
Yes, glass, steel, it depends of the properties. Yeah.
how do you think that you are representing well that correlation using properties for another material?
Well, I wanted to evaluate it. I wanted to evaluate the impact of the actual effective conductivity, even if the values would be, how can I say, like to see if the value of the actual effective conductivity has a significant impact on the description of in absence or on the rest conditions. So that's why I decided to keep those values just to see, okay, that would be important or not. But when I estimated my values, yeah, these values were estimated under the experimental conditions I had. I mean, titania was the pellet semiconductor, not glass, and I could see similar values for, in this case, the glass that consider Botruba. So at least was under the same range of the materials he or she, I don't know, investigated, and that gave me a confidence to say, okay, these values are real, are not out of some magnitude order or something like that.
Okay, in that regard. Okay.
Mhm.
I have some doubts about the importance of having the experiment made without the flow of air.
Without
Here
the
in-
flow of air.
Yes, those experiments allow you to obtain what?
Yeah, the statistic contribution probably. Yeah, I don't have
The
a slide
static
here.
contribution.
Yeah, I don't have a slide here, but the correlation for the axial effective conductivity has two parts: the static contribution and also the dynamic contribution. The dynamic contribution is the one that considers the effect of the particle Reynolds, and the static contribution is without any flow. So with this static contribution, well, as the name is said, it captures the radial heat transfer mechanisms in absence of flow, and it's not the same as the conductivity of the material. I mean, it's not the conductivity of titania. It's kind of the same magnitude order, but this is because the actual, well, the effective conductivity captures different kind of mechanisms. I have a slide for that here. So, yeah, this one. So, for example, here, it has the conduction through the motionless fluid. I mean, the fluid that is not flowing in the bed. The conduction through the pellet, also in the case of very high temperatures, radiation, and the conduction through the pellet, right? The first 5 points are the static contribution. And then from 6 to 9 is the effect that the movement of the fluid has on the value of the radial effective, well, the actual or the effective conductivity. That's why I started with no flow to capture these 5 mechanisms, and these are not the same as the conductivity of the material.
Well, that sounds interesting. However, your correlation, if you go back to slide 19.
19? No. Yeah, this one.
Here at the right.
Yes.
The effective the static contribution seems negligible. When you pretend
yes.
That's why I say, well,
yeah,
when you calculate the effective conductivity.
Yeah, is negligible? Yes, under the operating conditions for this reaction. However, it also gave us some idea of the of the value that the radial effective conductivity will have when it reaches the wall.
Yes, but it's due to the Reynolds number, and that because the value of the conductivity.
Yes, but I mean the radial effective conductivity has a similar trend as the void fraction, and also as well, is the opposite of the fluid dynamics. And we know that in the wall, I mean, following the no-slip condition, we won't have any flow of the fluid, and that is the static contribution of
Yes, yeah, conceptually,
conceptual.
I agree. But
Yes,
from the correlation, the shape of the correlation and the term,
yes,
when you calculate the effective conductivity, it doesn't weigh too much
yes,
to the final value.
Yeah.
That's what I was questioning when I
Yeah,
saw
yeah.
that curve that doesn't have a significant value.
yes.
Okay, so let's continue. Okay. How do you expect the results that you have obtained with the equipment, the bench equipment for heat transfer?
Yes.
How do you expect those results to be affected by the ratio particle to diameter ratio? How do you expect? Is
So
it valid for 10?
well, yes. For example, in this same slide, yeah. For example, the void fraction. If I calculate the void fraction, we will see that void fractions. Well, some with high void fraction are at a dimensionless radial position of 1. This means at the size of one pellet from the
Yes.
wall to the center, and in the wall zone. So if we look at the experimental data, we won't see like a perfect line as this at the simulations.
Yes.
We'll see like ups and downs, and most of these downs are here in the dimensional radial position of 1. So if I could have another to particle diameter ratio, I could expect similar trends like ups and downs, yes, and those trends would be also they're affected by the void fraction. So in the sense of having different to particle diameter ratios, in the experimental data that I could expect is in that way.
It's in that way. My question comes because you state in your work that it's concerned with the case of tube diameter to particle diameter
Yes.
below 8.
Ah, yes, yes.
And all the experiments and simulations offer a different ratio of diameter of the tube to the
Yes.
particle. Where does 8 come from? I
Yes.
didn't
The 8 is
understand how
the
does 8 come from?
yeah, the 8 is kind of empirical number that based on researchers, well, based on the research done in literature, when the tube to particle diameter, the tube to particle diameter ratio becomes lower than 8, this void fraction effect that is also the fluid dynamic effect that is also a temperature gradients in the wall zone becomes more and more difficult to how can I say, to assess. If the tube to particle diameter ratio is higher than 8 or higher than 10, we can use plug flow. We can use constant parameters for the effective conductivity, and the results will not be so different as if we consider fluid dynamics or we're considering it so the local effective conductivity. So it becomes important when the number is lower than 8.
So these results are good for any
Yes.
ratio below 8.
Yes, and this geometrical configuration is considered for highly exothermic reactions in industry because the impact that the void fraction has on fluid dynamics and the fluid dynamics impacts in the convective term of the heat transfer mechanisms, and it removes the heat in a better way, at least for the purposes of cooling the reaction, instead of having to particle diameter ratio higher than 8, higher than 10. I mean, it would be real difficult to dissipate the heat on those systems than instead of the low to particle diameter ratios.
Okay. Well, Thank you. I have just a couple of
Yeah.
more questions. And in the experimental setup,
Yes.
this experimental setup, there is an issue in terms of the heating at the wall.
Yes.
There is a maximum temperature at the center.
Yes.
Did you deal?
Yeah.
How
Here.
did you deal with this?
Yes.
situation?
Yeah. I didn't explain very much this system. So looking at the figure, well, looking at the packet bed from the left. So in the lab here at one, we have this packet bed, as you can see in the pictures showed in the slide. So it's a bench scale packet bed of ½ meter with some thermal wells set at different axial positions, and then as you can see in the picture from top left, I inserted the thermocouple to the wall first, and then I was like filling the tube, like yeah, inserting the thermocouple, filling, and then inserting thermocouple and filling the packet bed with these titania pellets, and then the thermocouple at the center of the bed was connected to a control to keep the temperature always the same, or 180 degrees, if I remember correctly. And because with the flow of the gas, in this case air, the temperature will start changing. And then I wanted to repeat this experiment at different radial positions, because I was removing little by little the radial position of the thermocouples, and I also obtain experimental data at all these, let's say, temperature field, radial position, axial positions at different times in the transients. So all the thermocouples were like removing little by little, but the temperature the one in the temperature control. This because I wanted to repeat the same experiments. This is for the bench scale. For the industrial scale, I mean, took in some experimental data from the research group. It's the same bed. Well, I mean, the same geometrical configuration, to particle diameter ratio. Even the catalyst, the pellets are the same. Everything is the same. However, the heating is different. Here is a salt bath, and the temperature in all the surrounding the tube is basically the same. There was also a temperature control, and yeah, that's all I could say from the way how the experiments were done and the role of the temperature control.
But in the case on the right.
On the right there is the infrared lamp, and here, well, we don't have a temperature control because as we discussed before, temperature didn't reach more than, well, in absence of flow, I think it was like 300 degrees, but then with a little bit of flow, it decreased to 100 degrees, and then 80 degrees, 60 degrees, until room temperature are really, really high flows.
Okay, thank you. Well, my final question.
Yes.
There is a work from Castillo and co-workers from 2007. Yes, they use very similar equipment. And what, considering the work where you determine the pressure drop in the fixed bed.
Yes.
You have recalculated the constants alpha and beta from Ergon's equation.
Yes. Here.
Yeah. What puzzles me is that the values that you obtain are about twice the value of those reported in that work.
Yes.
Considering the same equipment, the same catalyst particles.
Yeah, yes.
Did you sit down with your supervisor and try to explain, hey, what's happening here?
Yeah. Actually, it's not the only it's not the only paper that has this difference.
Uh-huh.
What I found was that
The same equipment.
yeah, but
Same
but,
system.
yeah, sometimes, well, what I found is that there were pressure drop difference. Well, pressure difference, and there was not the dividing for the length of the length of the system. And if you see here, the length of the system is half meter. So maybe they could explain the twice value. And also I compare this experimental pressure drop.
It's alpha and beta, not the pressure drop. The
For the alpha
constant-
and beta.
the
Yeah,
alpha,
because
the alpha and beta.
yeah, because there is also
Yes,
an error
alpha,
on
beta,
the
those parameters.
yeah.
They differ significantly.
Yes. Well, what I could say here is that alpha, I don't remember if it was alpha and beta, but they are really sensitive to changes. Of course, there was no correlation between those two parameters when I did the estimation. Yeah, I'm not sure if at which particle Reynolds these experiments were carried out. Yeah, I can attribute that difference of the parameters to the sensitivity of these parameters. That's what I could say now.
Do you remember the operating condition used for
this?
these
Yes.
parameters?
The flow.
In terms of the inlet velocity. Remember
Inlet
that we used
velocity.
normal condition, and when we did several years ago, we did
Yeah.
this at the average temperature at used for the reaction.
Yes. Was something. Yeah.
Maybe you don't remember
No.
discussion, but okay.
Yeah.
Yeah. Okay.
Okay.
Well, yes. Thank you. Well, I will ask the examination board members if they have any other questions or
Yeah.
examinee.
Take a
And then-
final comment.
No, in my case, no additional question for in my case.
Okay.
Yeah.
Thank-
Maybe
Anybody else?
switch here. Yeah.
No? No. So if you
I don't know if yours have, but I
you
a
have
final comment. It's
so you have Castillo, Professor Castillo.
Mhm.
okay. I don't have a question, but I would like to say some words just to finish this process. It has been hard. But okay, we are here. Okay, first, I would like to express my gratitude to Alejandro for the outstanding work he accomplished during his PhD research stay. You did an excellent presentation and defense today. Yes, congratulations. Regarding research contribution of Alejandro, I would like to comment the following. In the outcome reaction, despite it being preliminary, he shed light on the promising nature of the reaction, highlighting its potential to be further explored, but with the full scope of reaction engineering. I think that we all agree on that. In his second contribution on the OEDH of ethane, Alejandro not only focused on modeling the industrial reactor, but also provided invaluable insights into how transfer phenomena influence kinetics in this complex system. He went further by developing innovative methodologies to characterize fluid dynamics and heat transfer, approaching this challenge with a fresh perspective, tackling issues that remain significant obstacles in reactor engineering for selective oxidation. Achieving 3 publications from these studies is an exceptional accomplishment, reflecting his expertise and unwavering dedication through his PhD journey. I would like also to thank Joris for his unwavering support in this joint PhD. Thanks to Jerome for his collaborative work on this PhD thesis. And my heartfelt appreciation goes to the jury for accepting the invitation to evaluate Alejandro's work. I do appreciate your work, your support, and enjoyed your questions. Finalmente, quiero felicitar a la familia de Alejandro, ya que un logro como el de hoy no es fácil. Creo que está aquí tu familia,
Sí.
¿verdad?
Sí.
Felicidades. Creo que un logro como el de hoy no es fácil, especialmente bajo las circunstancias que implica un doctorado mixto, aunado a la pandemia que tuvimos y todos los efectos secundarios que tuvo, ¿no? Creo que es un logro para todos, de eso estoy seguro, para toda tu familia. Yo creo, Alejandro, que solo una persona con coraje y que vence miedos y obstáculos, además de tener objetivos claros, puede superar todos estos desafíos y ahora estamos aquí. Así que felicidades a ti y a toda tu familia y espero que la decisión de que apruebes la tesis sea positiva.
I would like to ask the audience if you have any question. No. Joris?
I'm not sure.
Does Professor Joris has?
Yes, if I may, maybe also for a short while. So, can you hear me properly?
Yes.
Yes. Yeah.
Okay. So, well, Alejandro, I would also start by I would also like to start by congratulating you for the work you have done, for the results you have achieved. And yeah, it's a pity I couldn't make it to come to be with you in Mexico today. But yeah, it has been a heavy conference season already this summer, and yeah, making the travel would have been a bit too heavy. But I reserve that for a next occasion because I would definitely like to also see you in your home environment, and of course not only you but also Omar. For whom it has been a pleasure to work with and do this joint project with you, and in fact not only with you but also with Carlos Camacho, who obtained his degree a few months ago. When I think back of your work and working with you, well, having activities from both sides, having topics from both sides, although related, it has been a bit well, it has been a bit challenging to get into it. But I do remember once the train got rolling, that well, it was rolling quite well, and it was sometimes challenging to keep up with everything. And that having a good assessment of what has been done, well, was sometimes challenging, but I think it has really led to very nice results. And led to 3 outstanding publications, and indeed we will have to see the citations, but I'm confident that will also work quite well. And of course, there's not only the science, there's also the personal and the social side, and I think, well, there I cannot really comment on things at the Mexican side, but at the Ghent side, I think you were one of the leading and one of the well-valued members of the LCT football team, which made it this year, well, which won the 2 cups that were possible. And although in the last games you were probably not there anymore, but I think you still had a very yeah, important contribution at the start of that. But okay, the LCT football team is not the one I'm most involved with. I'm more the runner, and with my knee I have to keep a straight. Yeah, I need to go straight, and all the turns and the things in football are a bit dangerous. But also in the other social events which we had, well, you participated well, and you were not afraid to take the lead in there. So I'm quite sure. Well, we miss you already, and I'm quite sure you will be missed even more. Although of course there is also a new generation which will take over. And I think you have a nice future ahead of you in the first stage, still at UM. But I'm quite sure other and further nice opportunities will be there for you. And I wish you all the best in your future career. And I'm quite confident our paths will still cross there. So congratulations, thanks again, and also thanks to Omar.
Thank you.
Thank you. Passager?
I'm not sure if Jeroen is.
Maybe we can ask him.
Yeah.
Yes.
Jeroen?
Jeroen is there?
Yeah, Alejandro, also congratulations from my side. It's been a pleasure working with you all this time. Not only working, as you already said, also a lot of social aspects, which indeed you will be missed in this respect. And I remember I have an outstanding invitation for the next World Cup, which will be organized in Mexico. So I'm sure our paths will cross again, Alejandro.
Okay.
Next year.
Okay. Okay, thank you very much. Well, thank you. There's nobody else that's going to participate. Okay, so we have ended with the interrogation. And so after this, the examination board will deliberate in private. So we ask Mr. Romero to please momentarily leave the room as well as an audience. Omar,
Ya me quedo sin. Nada más que le iba a dar. Vendió. Ah, es que no sé. Porque fíjate que no se presenta públicamente. Ah, mira. Sí, nos va a mandar una sala privada. A ver, hay nada más que. Sí, no, pues,
I think the others are still in the breakout room. I think that was the most complex part of the defense.
Oh, yes. But at least we got it, huh?
Definitely. Yeah.
Now all
Right.
back.
And we need to learn all these different softwares.
Exactly.
It's improving, huh?
Yeah,
First, there was a strong improvement. Now it's a small improvement, but still,
Yeah.
it's improving.
we are ready for the next
To the
epidemic.
next level, huh? AI.
En la Ciudad de México se presentaron a las 8 horas el día 20 del mes de agosto del año 2024 en la unidad Iztapalapa de la Universidad Autónoma Metropolitana los suscritos miembros del jurado: Dr. Richard Steve Ruiz Martínez, Dr. Gamaliel Che Galicia, Dr. Kai Olaf Henriksen, Dr. Max Seis, Dr. Héctor Fernando Puebla Núñez. Bajo la presidencia del primero y con carácter de secretario el último, se reunieron a la presentación de la disertación pública cuya denominación aparece al margen para la obtención del grado de Doctor en Ciencias Ingeniería Química de Alejandro Romero Limones. Y de acuerdo al artículo 75, fracción 4 del Reglamento de Estudios Superiores de la Universidad Autónoma Metropolitana, los miembros del jurado resolvieron aprobar. Acto continuo, el presidente del jurado comunicó al interesado el resultado de la evaluación y en caso aprobatorio le fue llamada la protesta. La protesta va a ser leída por el doctor Castillo.
Protesta usted, doctor Alejandro Romero Limones, empeñarse con honestidad intelectual y rigor inquisitivo en su carrera, con apego a las normas éticas, académicas y profesionales, utilizar su talento y la formación adquirida en provecho de la humanidad y en particular de la sociedad mexicana que sustenta esta casa de estudios y contribuir con su valor y ejemplo a mantener en alto el nombre de la Universidad Autónoma Metropolitana. Si así lo hiciese, que la universidad y la sociedad mexicana se lo premien, pero si no lo hiciese así, que se lo demanden. A nombre del director de la División de Ciencias Básicas e Ingeniería, reciba usted las más sinceras felicitaciones. Felicidades.
At this point, the exam has concluded, and so I would like to thank the members of the examination board for their participation, and congratulations, finally. Yes, that's all.
Felicidades, Alejandro. Congratulations.
Congrats,
Thank you,
man.
and congratulations.
Yes, well done.
Congratulations.
Congratulations.
Yeah, they will still take a picture with us, I assume.